The universal speed limit. Why nothing can break the light barrier, and what breaks if it does. On September 22, 2011, scientists at CERN made an announcement that sent shockwaves through the physics community. They had detected particles, neutrinos, traveling faster than light. Not by much, just 60 nanoseconds faster than light would take to cover the same 730-kilometer distance from CERN in Switzerland to the Gran Sasso laboratory in Italy. A difference of 0.0025%, barely measurable. But if true, it would shatter the foundation of modern physics. Because the speed of light isn't just a speed limit, like a highway speed limit that you can break if you're willing to risk a ticket. It's woven into the fundamental structure of spacetime itself. It's the conversion factor between space and time, the maximum speed of causality, the cosmic constant that makes the universe logically consistent. If something can travel faster than light, then effect can precede cause. Time travel becomes possible. Simultaneity becomes meaningless. The laws of physics become self-contradictory. Reality itself unravels. Einstein's entire framework, special relativity, general relativity, E equals mc squared, depends absolutely on nothing exceeding light speed. Break that barrier, and you don't just break a rule, you break the universe. The physics community reacted with skepticism bordering on disbelief. Extraordinary claims require extraordinary evidence, they said. The CERN team must have made an error, a miscalibration, a computational mistake, a subtle systematic bias. And they were right. 6 months later, CERN discovered the problem. A faulty fiber optic cable connection had introduced a 73 nanosecond timing error. When corrected, the neutrinos traveled at exactly light speed, as relativity predicted. The speed limit held. Reality remained intact. But the episode revealed something profound. Physicists were terrified that the measurement might be correct. Not excited, terrified, because faster-than-light travel doesn't just violate one equation, it undermines the entire logical structure holding reality together. Today, we explore the ultimate cosmic speed limit, not just what it is, 299,792,458 meters per second, but why it exists, why it's absolute, and what would happen if something could break it. We'll discover why light speed is the universe's most fundamental constant, why it connects space and time inseparably, and why even hypothetical faster-than-light technologies, warp drives, wormholes, tachyons, face barriers that might be impossible to overcome. And we'll explore the terrifying question: if the speed limit could be broken, would we want to break it? Or would the consequences, causality violation, paradoxes, the potential unraveling of physical law, be too catastrophic to risk? This is the story of the universe's ultimate boundary, and why crossing it might destroy everything. Let's begin. Act 1. Why the limit exists. The speed of light wasn't always considered a universal limit. For most of history, people assumed light traveled infinitely fast, that distant events were visible instantly, that there was no delay between something happening and someone seeing it happen. The first serious attempt to measure light speed came in 1676, when Danish astronomer Ole Romer noticed something strange about Jupiter's moons. Their eclipses occurred earlier than predicted when Earth was moving toward Jupiter, and later when Earth was moving away. Romer realized light takes time to travel. The delay depended on Earth's position. From this, he calculated light speed at approximately 220,000 kilometers per second, not perfect, but remarkably close for 1676. For the next 2 centuries, scientists measured light speed with increasing precision. By the late 1800s, they knew it was approximately 300,000 kilometers per second in vacuum. But they assumed this was just light speed through some medium, the luminiferous aether, a hypothetical substance filling all of space through which light waves propagated like sound waves through air. And they assumed different observers would measure different speeds depending on their motion through the aether. If you moved toward a light source, you'd measure light traveling faster. If you moved away, slower. Just like sound from a moving car sounds different depending on whether you're moving toward or away from it. In 1887, Michelson and Morley tested this assumption with exquisite precision. They built an interferometer, a device that splits a light beam, sends the 2 halves in perpendicular directions, then recombines them to create interference patterns. If Earth is moving through the aether, light should travel at different speeds in different directions, creating detectable shifts in the interference pattern. They found nothing, 0 shift. No matter which direction they measured, light always traveled at the same speed, exactly 299,792 kilometers per second in vacuum. This made no sense. How could light have the same speed for all observers regardless of their motion? Physicists tried various explanations. Maybe Earth drags the aether along with it. Maybe the aether doesn't exist, but light propagates through some other mechanism. Maybe the measuring instruments contracted in the direction of motion, hiding the speed difference. All these explanations were ad hoc, inelegant, unsatisfying. Then, in 1905, a 26-year-old patent clerk named Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies. Einstein's radical proposal: stop trying to explain why light speed appears constant, accept that it's constant, make it a postulate, a fundamental axiom from which everything else follows. Einstein's 2 postulates were simple. The laws of physics are the same in all inertial reference frames moving at constant velocity. The speed of light in vacuum is the same for all observers, regardless of their motion. From just these 2 postulates, Einstein derived special relativity, a complete framework explaining how space, time, mass, and energy behave at high velocities. And the consequences were staggering. First consequence: time dilation. If light speed is constant for all observers, then observers moving at different velocities must experience time at different rates. Imagine you're on a spaceship moving at 90% light speed. You shine a flashlight forward. According to you, the light travels away from you at light speed, 299,792 kilometers per second. But according to someone watching from Earth, the light should travel at light speed relative to Earth, not relative to your moving ship. Yet it can't travel at 1.9 times light speed, your ship's speed plus light speed. The speed must be the same, 299,792 kilometers per second. How can both be true? The only resolution: time on your ship must flow slower than time on Earth. From Earth's perspective, your clock ticks slower, your movements appear in slow motion, your heartbeat slows. This compensates for your high velocity, ensuring light still travels at c relative to both you and Earth. This isn't an illusion or measurement artifact. Time actually flows at different rates for different observers. Astronauts on the International Station age slightly slower than people on Earth, measurably, verifiably slower. GPS satellites must account for time dilation, or their positioning data would drift by kilometers per day. Time is not absolute, it's relative, dependent on velocity. Second consequence: length contraction. If you travel at 90% light speed, distances in the direction of your motion contract from your perspective. A 1 light-year journey becomes 0.436 light-years in your reference frame. This also ensures light speed remains constant. If distances contract and time dilates in precisely coordinated ways, light always travels 299,792 kilometers per second, regardless of the observer's motion. Space is not absolute either. It's relative too, dependent on velocity. Third consequence, mass increase. As you accelerate toward light speed, your mass increases. Not your rest mass, that remains constant, but your relativistic mass, the mass as measured by observers watching you move, increases without limit as you approach light speed. At 90% light speed, your mass is 2.29 times your rest mass. At 99% light speed, 7.09 times. At 99.9999% light speed, over 2,000 times. The closer you get to light speed, the more massive you become, the more energy required to accelerate further. To actually reach light speed would require infinite energy. This is why nothing with mass can reach light speed. It's not a technological limitation, it's a fundamental law of physics. Fourth consequence, E equals mc squared. Einstein showed that mass and energy are equivalent, different forms of the same thing. The energy content of an object is its mass times the speed of light squared. Why c squared? Because c is the conversion factor between space and time, and energy is fundamentally related to motion through spacetime. This equation explains nuclear energy, particle annihilation, and why the universe contains matter at all. It's the most famous equation in physics, and it only makes sense if light speed is constant and fundamental. All of this, time dilation, length contraction, mass increase, E equals mc squared, follows logically from the single assumption that light speed is constant for all observers. But why is light speed constant? What makes it special? The answer lies in the structure of space-time itself. Space-time isn't just space and time existing side by side. It's a unified four-dimensional fabric where space and time are interconvertible, connected by the speed of light. In space-time, every object travels at exactly the same total speed, the speed of light, not through space, but through space-time. When you're sitting still, not moving through space, you're moving through time at maximum rate, traveling into the future at 1 second per second, covering distance c through the time dimension. When you move through space, you trade some of your motion through time for motion through space. The faster you move spatially, the slower you move temporally. But your total speed through space-time remains constant, always c. Light itself moves at c through space, which means it doesn't move through time at all. Photons don't age. From a photon's perspective, if photons could have perspectives, no time passes. A photon emitted from a distant galaxy billions of years ago experiences no duration. From its perspective, emission and absorption are the same instant. The speed of light isn't the speed of light specifically, it's the speed of causality, the maximum rate at which information, influence, or interaction can propagate through spacetime. Light travels at this speed because photons have zero rest mass. Anything with zero mass must travel at exactly c. Anything with mass must travel slower than c. The speed limit is built into the geometry of spacetime itself, and this creates a fundamental cosmic structure, the light cone. Imagine spacetime as a graph with space on the horizontal axis and time on the vertical axis. Your current position is a point, here and now. From that point, two cones extend, the future light cone, all events you can possibly influence, and the past light cone, all events that can have influenced you. The edges of these cones represent paths light takes through spacetime. Everything inside your future light cone is causally accessible. You can send signals there, travel there, effect events there. Everything outside is causally disconnected. No signal you send can ever reach those events. This structure, the light cone, defines what causality means in our universe. Cause always lies in the past light cone. Effect always lies in the future light cone. Break the light speed limit, and you break the light cone. Travel faster than light, and you can exit your future light cone, entering regions of spacetime that should be causally unreachable. And that's when the paradoxes begin. Act 2. What breaks when the limit breaks? Part A. Causality violations. Let's imagine you've built a faster-than-light spacecraft. Not through any known physics, this is purely hypothetical, but somehow you can travel at twice the speed of light. What happens? The first problem, you can travel backward in time. Here's how. Suppose you're on Earth and your friend is on a space station moving away from Earth at 80% light speed. You and your friend synchronized clocks before they left, and you've been communicating via normal, light-speed radio. Now you get in your FTL ship and travel to the station at twice light speed. From Earth's perspective, this takes you half the time light would take. But here's where relativity creates problems. From your friend's perspective on the moving space station, because of relativity of simultaneity, the moment you arrive at the station is before the moment you left Earth. Let me explain that more carefully. In relativity, simultaneous isn't absolute. Events that are simultaneous in one reference frame are not simultaneous in another frame moving relative to the first. When you depart Earth, your departure is simultaneous with some specific clock reading on the station in Earth's reference frame. But in the station's reference frame, moving at 80% light speed, your departure is simultaneous with a different clock reading, one that's in the past relative to the station's current time. If you travel faster than light from Earth to the station, you can arrive at the station before the time that was simultaneous with your departure in the station's frame. Which means, from the station's perspective, you arrived before you left. Now here's where it gets worse. You can use this to send a message to the past. Once you're at the station, your friend sends an FTL signal back to Earth at twice light speed. This signal arrives at Earth in the station's reference frame before you originally departed. You've created a causal loop. You leave Earth, you arrive at station, friend sends signal back, signal arrives at Earth before you left. You could receive your friend's message, learn what the FTL signal says, and then decide not to make the trip. But if you don't make the trip, your friend can't send the message. But if your friend doesn't send the message, you have no reason not to make the trip. Paradox. This isn't some obscure edge case. It's a fundamental feature of faster-than-light travel in relativistic spacetime. FTL travel necessarily enables time travel to the past, and time travel to the past necessarily creates paradoxes. There are various proposed resolutions. The Novikov self-consistency principle. Time travel is possible, but you can only do things consistent with what already happened. You can't create paradoxes because the universe somehow prevents you, through quantum probability, through coincidence, through mechanisms we don't understand. The many worlds interpretation. When you change the past, you create a new timeline branching from that moment. You don't change your original timeline. You create a parallel one. No paradox, but also no way to affect your own history. The chronology protection conjecture. The laws of physics somehow prevent time travel, even if FTL is possible. Whenever conditions arise that would permit closed time-like curves, time machine scenarios, quantum effects produce infinite energy density that destroys the time machine. None of these resolutions are fully satisfying. The cleanest solution is the one relativity already gives us. FTL is simply impossible. The speed limit isn't arbitrary, it's the boundary protecting causality. Break the speed limit and you break cause and effect. The universe becomes logically inconsistent. Events can influence their own causes. The future can determine the past. Reason itself fails. But perhaps you're thinking, what if we're clever? What if we find a loophole? This is where the real creativity begins. Physicists have explored various hypothetical methods for effectively traveling faster than light without technically breaking the local speed limit. Each faces its own insurmountable obstacles, but the obstacles are fascinating. They reveal deep truths about the structure of spacetime. Let's examine the most famous loopholes: wormholes, warp drives, and tachyons. Each represents a different strategy for circumventing the light speed limit, and each, when examined carefully, either requires impossible physics or leads to devastating consequences. Starting with the most elegant, wormholes.
Part B. The impossible solutions. Wormholes, shortcuts through spacetime. A wormhole is a hypothetical tunnel connecting two distant points in space, like folding a piece of paper and poking a hole through, creating a shortcut between locations that are far apart on the paper's surface. In general relativity, wormholes are mathematically possible. The equations allow solutions where spacetime curves back on itself, creating these tunnels. The Einstein-Rosen bridge, first proposed in 1935, is the simplest wormhole solution. It connects two black holes through a throat, potentially allowing travel between distant regions of space. But there's a fatal problem. The Einstein-Rosen bridge is unstable. As soon as anything tries to pass through the wormhole, even a single photon, the throat collapses faster than light can cross it. The wormhole pinches off, trapping anything inside. To keep a wormhole open, you need exotic matter, matter with negative energy density, creating repulsive gravity that pushes the throat open rather than collapsing it. Does exotic matter exist? Quantum mechanics says yes, sort of. The Casimir effect creates negative energy density between two conducting plates in a vacuum. Virtual particles in the quantum vacuum have negative energy in certain configurations. But the amounts are tiny, far, far too small to hold open a macroscopic wormhole. To create a human traversable wormhole would require exotic matter equivalent to the negative mass of Jupiter. We have no idea how to create, contain, or manipulate exotic matter on that scale. It might be fundamentally impossible. Quantum field theory suggests there are limits to how much negative energy can accumulate in a region. Even if you could build a stable wormhole, it creates the same causality problems as FTL travel. If one wormhole mouth is accelerated to high velocity and brought back, relativity of simultaneity means the two mouths connect different times as well as different locations. You could enter one mouth and exit the other in the past. Time machine, paradoxes, causality violation. The universe might have a built-in defense. The chronology protection conjecture suggests that quantum effects create infinite energy density at the moment a wormhole becomes a time machine, destroying it before causality can be violated. Warp drives, moving space instead of moving through space. In 1994, physicist Miguel Alcubierre proposed a different approach. Don't travel through space faster than light. Instead, move space itself. The Alcubierre drive would compress spacetime in front of a spacecraft and expand spacetime behind it, creating a warp bubble that carries the ship faster than light, while the ship itself remains stationary relative to local spacetime. It's like surfing. You're not moving through the water faster than the wave can travel. You're riding the wave, letting it carry you.
Crucially, nothing inside the warp bubble moves faster than light locally. You're not breaking the speed limit, you're exploiting spacetime's flexibility to carry you faster than light globally. But again, exotic matter. To create the warp bubble requires negative energy density in a specific geometric configuration around the spacecraft. The energy requirements are astronomical, equivalent to the total mass energy of Jupiter converted to exotic matter. Recent refinements have reduced this to merely a few solar masses of exotic matter, which is still impossibly large. And even if you could build it, there are additional problems. You can't steer. The warp bubble causally disconnects you from the spacetime outside. You can't send signals forward to stop or change course. Particles accumulate at the warp bubble's leading edge, creating deadly radiation that would incinerate anything at your destination when you arrive. The bubble might be catastrophically unstable, collapsing at the slightest perturbation. And of course, the warp drive creates time travel possibilities. If two warp bubbles pass each other at relativistic velocities, passengers can use the bubbles to travel to their own past. Same causality violations, same potential paradoxes. Tachyons, particles born faster than light. A tachyon is a hypothetical particle that always travels faster than light, not by accelerating past light speed, but by existing in a state where FTL is its natural velocity. In special relativity, if such a particle existed, it would have imaginary mass equal to a real number times the square root of -1. This sounds absurd, but it's mathematically consistent with relativity's equations. However, tachyons create immediate causality problems. A tachyon traveling faster than light can be observed as traveling backward in time in certain reference frames. Moreover, if tachyons exist, they should be everywhere. The vacuum should spontaneously create tachyons continuously, radiating energy at an infinite rate, leading to vacuum instability. We've never detected tachyons. Their absence is evidence that they don't exist or can't exist in our universe. Every loophole leads to impossibility. Every method for circumventing the light speed limit either requires impossible materials, creates catastrophic instabilities, or violates causality. The speed limit holds, not by coincidence, but by necessity.
Act 3. Why the universe needs the limit. Part A. The cosmic structure. Let's step back and ask a deeper question. Why does the universe have this limit? Why not allow infinite speed, instant communication, action at a distance? The answer lies in the fundamental architecture of reality. The speed limit isn't an arbitrary rule imposed on the universe. It's a structural feature necessary for physical law to be coherent. First, causality requires a speed limit. Without a maximum speed for information propagation, cause and effect become ambiguous. Imagine a universe with instantaneous communication. You're on Earth, your friend is on Mars. You send a signal that arrives instantly from your perspective. But instantly is reference frame dependent. From the perspective of an observer moving at high velocity, your signal arrives before it was sent. Cause and effect reverse. This isn't just philosophically troubling, it makes physics impossible. Physical laws describe how causes produce effects. If cause and effect can reverse, laws become meaningless. The speed limit establishes absolute causal order within light cones. Events inside your future light cone are definitively in your future. Events outside are causally disconnected, neither past nor future, but elsewhere. Second, locality requires a speed limit. Locality is the principle that physical interactions happen at specific locations. Objects interact by direct contact or through fields propagating from one location to another. Without a speed limit, locality fails. A particle here could instantly affect a particle there, with no propagation, no mechanism, no intermediate process.
This violates not just relativity, but quantum field theory, our most fundamental description of particles and forces. In quantum field theory, all interactions are local, mediated by force-carrying particles, photons for electromagnetism, gluons for strong force, etc., that propagate at finite speeds. Non-locality would require abandoning quantum field theory, and with it, our entire understanding of particles, forces, and matter. Third, energy conservation requires a speed limit. In relativity, energy and momentum form a four-vector. Energy is the time component, momentum the space components. The magnitude of this four-vector is the particle's rest mass. This unification only works if there's a maximum speed relating energy and momentum. That speed is c. Without the speed limit, energy and momentum become independent, energy conservation becomes frame-dependent, and the foundations of thermodynamics collapse. Fourth, space-time structure requires a speed limit. General relativity describes gravity as space-time curvature. Mass energy curves space-time, and objects follow curved paths, geodesics, through that curved geometry. The curvature propagates at the speed of light. When a massive object accelerates, the change in gravitational field spreads outward at c as gravitational waves. If information could propagate faster than c, gravitational effects would have to propagate faster too. But then the field equations of general relativity become inconsistent. They predict infinite energies, acausal influences, logical contradictions. The speed limit is woven into Einstein's field equations. Remove it, and general relativity collapses. Fifth, information theory requires a speed limit. Information is physical. Every bit of information corresponds to a physical state, an arrangement of particles, a configuration of fields, a pattern in space-time. The Bekenstein bound states that the maximum information content of a region of space is proportional to its surface area divided by the Planck area. This bound only makes sense if information can't propagate faster than light. FTL information transmission would allow infinite information density in finite volumes, violating the Bekenstein bound and creating black hole paradoxes. The speed limit isn't one isolated rule. It's the keystone holding together causality, locality, energy conservation, space-time geometry, and information theory. Remove it, and the entire edifice of physical law collapses. The universe doesn't just have a speed limit. The universe is a structure built around that limit. Light speed is as fundamental as the dimension of time, the conservation of energy, or the quantization of charge.
Now, concluding this universal paradox, we began by asking why nothing can travel faster than light, and what would happen if something could. The answer, the speed limit, isn't arbitrary. It's structural. It's woven into space-time's geometry, causality's logic, energy's conservation, and information's physical nature. Break it, and you don't just move faster. You break cause and effect, create time machines, violate locality, undermine physical law, and potentially unravel reality itself. The hypothetical methods for circumventing the limit, wormholes, warp drives, tachyons, all require impossible physics, exotic matter in vast quantities, or create paradoxes, time travel, causality violations, or both. Nature seems to have built-in protections. Wormholes collapse, warp bubbles are unstable, tachyons don't exist. The universe defends its own logical consistency. But rather than seeing the speed limit as a constraint, we should recognize it as a gift. It creates order from potential chaos. It makes chemistry, stars, planets, and life possible. It establishes cosmic horizons that make the universe comprehensible.
It offers time dilation as a way to explore vast distances within human lifetimes. The speed limit is why the universe makes sense, why physical laws are discoverable, why we exist to ask these questions. Einstein gave us more than equations. He revealed reality's architecture, a structure where space and time interweave, where matter and energy unify, where everything is connected through geometry rather than separated by emptiness. And at the center of that structure stands the speed of light, not just photons moving through space, but the fundamental constant relating space to time, energy to momentum, cause to effect. It's the universe's ultimate speed limit. But more than that, it's the speed at which reality is, the rate at which causality propagates, information transfers, and existence unfolds. We can't break it. We shouldn't want to, because breaking it means breaking everything. The universe is vast, the mysteries are endless, and the speed limit, that ultimate cosmic boundary, is among the most fundamental mysteries of all. Not because we don't understand it, but because understanding it reveals how perfectly, elegantly, inevitably reality is constructed. You cannot travel faster than light, but light speed connects you to everything, to distant stars whose light crosses the cosmos to reach your eyes, to the deep past encoded in ancient photons, to the fundamental structure binding space and time. You don't need to break the limit. You're already traveling at light speed, through space-time, through the dimension of time, toward an unknown future. The cosmic speed limit stands, absolute, inviolable, eternal. And in its permanence lies the stability of everything we are, everything we know, and everything we'll ever become.